Saxon Advanced Mathematics, lesson 121. With my students, I stop at 120 lessons. In fact, with many of my students who are going on to college level math, we stop at lesson 100, but I went ahead and completed the lessons through 120. For students online who may be using these videos and want to complete the full book, I went up to 120 and then I realized, oh, there's 5 more lessons. So I'm going to do these last 5 lessons, and those of you who are interested in finishing every single lesson in this big green book, here we are. I'm going to do it with you. Lesson 121 is kind of a quirky little lesson about graphs. It's not particularly complicated or hard. It's just kind of a funny little jigsaw puzzle of a lesson. What we're going to talk about, I'm going to draw these two, but I just want to show you the picture of what it looks like. We're going to talk about functions, also known as graphs, that are actually made up of several different pieces. That's why we call them piecewise functions. They're kind of composites. And so when we graph them, we'll write the equations of each one of these, but then the other part we have to be really careful about is writing the domain so that we are limiting each particular equation to the section of the function, also known as graphs, that we're trying to describe. All right, so this is what we're getting towards. And now I'll just show you the other one. See this one? It goes out like this, and then it goes like that. That's kind of weird. And then the third one we'll work on will be like this, where it has three separate pieces that do not connect. Okay, so sometimes they connect, sometimes they don't. Let's take a look at them in more detail. Example 121.1. Write the equation for this function. So even though we can quickly see, oh, there's actually different pieces to it, it's not just one thing, it is considered a single function. I'm making the scale on this fairly large because I want us to be able to see the details really well. So I'm just putting in the numbers that John has on his graph. That's what we'll do. I do recommend, especially in the beginning, when you're copying these, that you copy the picture carefully. Sometimes you can get away with just making a quick sketch, but not this time. All right, I'm going to use different colors for the different parts of the function. The first part has a solid dot here, and a solid dot here, and then a line that connects. So that we'll write one piece for that. Then there's a piece that goes up from here to the point 3, 1, and then that is a point, okay? And then this is blue, this is the same dot, it's solid, so it's solid for the blue piece and it's solid for the orange piece. That will be an interesting piece to write out. And then same thing up here. It's a solid point, so that means it's part of both the blue and the red. Okay, so now what we're going to do, now that we've identified the different chunks of this function, we're going to go through and write equations and domains for each one. So with the orange part, it goes here. It is, we can see that y is equal to -1. It's a horizontal line. Remember, horizontals are y equals and verticals are x equals. So this one is y is equal to -1, and that is when x is between 1 and 0 inclusive, right? So here's the equation of the orange line, and here's the domain that describes the part we're interested in. Okay, now, oh, I don't want green, I want blue. Now we've got a line that has a slope to it. So we're gonna have to figure out what that slope is. We know it's gonna be y equals mx plus b, something x plus something. We know that this is going to be the slope. It's going to be the rise over the run. So we go up 2 and over 2. Oh, that's 2 over 2, which equals 1. I'll write the 2 over 2. We'll simplify this. Now, what about the y-axis? We know the slope. We've got some points that this line goes through, but we don't have the b. So what we can do to solve for b is what we've always done. We'll take one of these points. Let's choose this one. Let's choose the point 2, 0. And then we'll plug it in. 0 equals 1, I'm reducing that, times x plus b. This is positive 2, so we subtract 2 from both sides, and we get that minus 2 equals b. So that means this is the equation of that line. And I'm going to simplify it down here. Y equals, this I can drop all together, right? And just write x, and I don't need plus minus 2, that's just awkward. Y equals x minus 2. For what values of x? Well, let's see, it goes between 1 and 3. And that's where we have to be careful, because we can see that this point is included in this function, but it also is included in the blue function. And then this point will be blue and also red. So as we write our domains, we're just being careful to reflect that. So this line is between 1, and 3, right? 1 and 3, it's inclusive at each of those points, so we want the equal sign. All right, so we've got the second one figured out. And then the third one, which I'm using red for, that's another flat line. So that's going to be another y equals, and let's see, it's y equals positive 1 for domains. Oh, now this one's is open-ended, right? So this is when x is greater than or equal to, because the dot applies to the red line too. Beautiful, right? So there we have written equations for each segment, each piece, if you will, and we've written the domain that describes exactly how much of this we want in our picture, and that's our final answer. Now I'm going to show you the way John writes it. I consider this to be perfectly lovely. What John does is he writes that y equals minus 1 if 0 is less than or equal to x is less than or equal to 1. That's this part. Then he writes y equals x minus 2 if 1 is less than x is less than 3. And then the third part, y equals 1 if x is greater than 3. And then what he does is he puts a system of equations, brackety kind of thing there, and he uses this as the format for presenting the final answer. The information is the same as what we generated in our 3 pieces. He's just given it a little bit more style. I think it looks good. All right? So getting from our answers to his answers is super straightforward. Okay, let's do another one. There are a total of 3 examples in this lesson. Example 121.2. Write the equation for this function. I'll draw it for you. I showed you the picture of it. John wrote in a ton of numbers. I'm not going to write in so many numbers. That'll make me crazy. This is solid. This comes up, let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, oh no, 4, 5, 6. It's not quite the right size. Let me draw it over. I want it to be good. One, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Okay, this is the point he wants us to mark. It is the point -8 Oh, I graphed it wrong. I'm sorry. I'm getting turned around. It's not this point. It's 1, 2, 3, 4, 5, 6, 7. It's -8, 7. That's the point we want. Not this one, it's this one. -8, 7. And what we have is a solid dot here at 0. And then we have that point clearly identified. And then we have an arrow continuing on in that direction. We also have over here, so this is 7 up here, right? So this must be 6, 5, 4, 3, 2, 1, yay. We have an open circle here, and then we have a line that goes straight across. Right? So we're gonna write these two sections. We're gonna use domain to limit the equation to what we want, and then we're gonna rewrite the answer in the super cute way that John showed us last time. All right, let's try this one. We see that it is a line, so we know it's gonna be y equals mx plus b. We'll fill in those blanks. Let's see, the slope is always the rise over the run. So we can go from this point to this point. We can see it's gonna be a sink over a run, right? The run always goes to the right. So let's go down and then across. We will go down 7. 1, 2, 3, 4, 5, 6, 7. And then we'll go 8 this way. So it will be -7/8 is our slope. It's not the cutest slope I ever would want to have, but it's okay. And then we want our y-intercept. Now this, we could take a point on this line and plug it into this and solve for b. We can do that, but we can also see that this line extends far enough that we can see where it crosses the y-axis. It crosses at 0. So we'll leave that off in our final draft, but we can see, as opposed to on this one, this blue line, we didn't see exactly where it crossed the y-axis. So we couldn't use that information. We had to solve for our b. We could solve for our b in this one, but because the line actually does come up to the y-intercept, we don't need to. We can identify it like this. Now, for what values of x do we want to apply this? Well, let's see. It's going to be for x's less than or equal to 0, right? Because it starts at 0, and then it goes into the negatives and it goes to an infinity. So it is x is less than or equal to 0. This is our domain restriction. Okay, then what about this up here? Oh, okay, this is a horizontal line. That is a y equals a plain number type slope. Here's how I remember it. When it's y equals, that feels pretty normal to me. We're used to having y over here by itself. That's just a nice flat country road where there are no hills. It's perfectly fine. It doesn't have a slope, but it's perfectly lovely to drive on. So it's y equals a plain number. If it's up and down, cars can't drive that way. That's when the equation starts to look weird. That's when we put x on the other side. And everything gets a little nutty if you try to drive your car up a straight line. I have a video in my Mathiness playlist on my channel that shows somebody with a Jeep in some sort of a like rocky desert trying to drive a car up an extremely steep cliff, and it's a good visual reminder that that just doesn't work as well. Driving on a flat road is much easier. Okay, so y equals 6, and let's see, that does not include 0, but it's numbers greater than 0. Make sense? So these are my two lines. These are my two domain limitations. So I'm going to just do this. I'm going to write the if here, and I'm going to put the bracket on it here. Now I've taken my notes and quickly transformed them into John's beautiful presentation. And I'm just double checking to make sure I got it right. And we did. Yay! And the moral of my messed up picture here is when you're graphing, don't tuck your picture too close to the edge of the page, because that if I would have just started over and I'd drawn that line shorter, then you can just add to it and edit your picture. But if you draw it squished up next to the edge, then you just have to start over. So don't be like me. Okay, this is the right answer. Yay. Now for the third problem, John is going to reverse the process a bit. Now he's going to give us this kind of information and ask us to draw the picture. All right, I'm down. Where are you? So it says graph the function, and then he's written it all out. So I'll copy it. If you were doing this problem, you wouldn't necessarily have to copy it. You could work from the book. What the heck did I just draw? I'll explain it to you in a minute. But it is an infinity sign with a minus in front of it. Y equals x if 0 is less than x, 2, and okay. Let's ignore that symbol for now. Let's look at each of these pieces separately. I have the advantage of being able to peek at the solution, and I know we don't really need the bottom half, we just need the top half. I'm going to use colors again to help us keep straight which piece is which. And I'm going to suggest that for now, we're just going to ignore that. Okay, so first we're going to do this part. Y equals 2, okay. And again, we're going to make this graph fairly big so that you can see all the pieces. I'm going to skip lines just to make it easier for you to see. Okay, y is equal to 2. There's my 2. If x is less than or equal to 0. So I can color this in. X is less than or equal to 0. I'm ignoring this part by now. Actually, I'm ignoring this other inequality. Okay, so we're just going to ignore that piece when we're graphing. And, oh, I used the wrong color. I'm so sad. This should be orange. Colored in. And then it's any values of x less than 0. So this is going to go like this. With an arrow, right? Because it's values of x that are less than or equal to 0. I've colored in this value. Can you see that? I know it's a little messy. Okay, so, and let me just put numbers on here. This is 1, 2, 3. This is the y-axis, this is the x. Boy, I haven't written that in a long time for you, but let's just put it on. X is less than or equal to 0. That should actually be there. Okay, so all of those values are good. Okay, now let's do the middle one. Y is equal to x. Okay, let's stop and think. What does that look like? The slope is an invisible 1 over 1, and the y-intercept is 0. So we start here, we go up 1 and over 1, and we can see that this is going to be that diagonal that comes out and stays right in the middle of this quadrant of the graph. This line we want to draw for values between 0, but that we want to have an open 0, right? We don't include the actual 0. And then it goes all the way to positive 2. So I'm going to put the numbers on the graph. And we know it's going to go up like this, and we're going to stop at 2 right here. We're going to include 2 so we can make that a colored in point, and then we will connect like so. This one is open, This one is closed. That one tells us to keep it open. That one tells us to close it, okay? Now we're ready for our third one. This one is red. Now, I don't like the way this one is written. The order is wrong, so I'm gonna rewrite that as y equals minus 1 over 1x plus 3. I feel much better about graphing that way. So we know that we want this point between, for values of x that are greater than 2. Now again, we're going to ignore this while graphing. We just don't need to think about that. It's a notation stylistic thing that I'll explain when we're done. While graphing. Okay. So for this one, we're going to figure out how to graph this line, and then we're going to take it only for values above 2. But let's figure out what the line will look like, because right now we don't have enough to go on, do we? Let's pick up, well, let's see. We don't know a point on that line. We know that it's going to be okay, let's do this. We have to figure out an x and a y so that we can solve this for b. We don't have a point on this line yet, right? All we have is the equation, part of the equation, but we don't have any points that fall on there. So, and we don't want to go up here to start graphing from positive 3, the y-intercept, because, well, I guess we could do that with a pencil, couldn't we? Or something else. Let me do that. I'm going to use a pencil, which I don't normally use. But that way we can see that we know we don't want the whole line. So I'm going to graph this. I'm going to go to positive 3. There's my first point. Then I'm going to go down 1 and over 1. That's going to be right here. And I know that my line, let me turn my page for a second. I think this will work. My line's going to go like that. Can you see the faint mark there? It's a little bit, let me just, I know where I want the point to come out, and I'm just a little bit off. There. Can I erase? It's really faint. I drew it very faintly with my pencil because I know we have a domain limitation on this. I don't want the whole line. I only want it for values of x that are greater than 2. So I go to 2 on the x-axis, and I circle where the line, it's super faint, but I sketched this line in with pencil. Now I go to the place where x equals 2, which is right here, and I go to my line, and that's where I want to start. I want an open circle here because I don't have an equal sign. Now I want to go ahead and include in my piecewise function all the values of x that are greater than 2. So I'm going to continue the line in the marker to show it's part of our function. Wow, that's kind of crazy, right? So let's review it. This first section was a vertical line. No, I'm sorry, horizontal. I used the wrong word. A horizontal line that includes the original value. The second piece was a line that we could extend into y equals mx plus b by just adding in the invisible pieces. And again, you could have taken a pencil and drawn the whole line in super faintly, and then just highlighted the section that we wanted to include, which was the part between 0 and 2 inclusive. That's another way you can say this. We want values of x between 0 and 2 inclusive. So there's 0, there's 2 inclusive, and we included all of those. This one, we had the y equals mx plus b straightened out, but we just had to rearrange the equation because that wasn't the right arrangement for graphing. We found the line, we graphed the line with pencil, and then we did the same thing. We went back and picked up just the part of the domain that we need. We want values of x greater than 2, so that's open, and then we extended, these are the values of x greater than 2. This is our final answer. Yay, happy days. Now, what's up with these little infinity signs? What would happen? Let's take a look at this. Minus infinity is less than x is less than or equal to 0. This is the new way of writing it, but what we have been writing is just x is less than or equal to 0, right? That's what this picture is describing. We're used to saying it this way. What we do is when we add this, this is useful for describing an interval. Okay, that's the mathematical phrase for what we're doing here. This does not describe an interval because it just shows less than. This describes an interval because it shows us that we want values for x that fall less than or equal to 0 and then toward infinity on the negative end of the spectrum. See, we're going toward negative infinity. It's just a way to refine our inequality to make it a bit more precise. And again, depending on the context of what you're doing, this might be helpful. Similarly, this one, we've just written this in the past as x is greater than 2. This has the same meaning, but this expression describes an interval. An easy way to think of what the interval is it's got 3 pieces and our x is between. But this is saying the very same thing. This is saying give us values for x that are greater than 2. This is values of x that are greater than 2 but less than positive infinity, which makes sense because we're moving in this direction. So that's positive infinity. So these two symbols don't change conceptually what we're doing. They just add, let me put that equal sign in there. They just add a little more nuance to our expressions, our inequalities, and they may end up being useful in future problems, spoilers, that we would want this written in interval format, and that's what we call this. Okay? Great. Subtle. The next and final topic, it does not have a problem, is a special function. It's called the greatest integer function. And this is one of those things that looks like it's going to be hard, but it's so easy, it's almost hard. Okay. So we have a nice big graph, and I'm going to double space my grid again so we have lots of room to look at the details here. Remember that a function is a word that can be used to describe an equation or a graph, because equations can be graphed. Function is a word that works for both of them. What we're looking for here let me draw the first part of it for you. I want to start here. This is 1, this is 2, this is 1. This part of the picture is saying, look at all of these different numbers that fall between 1 and just less than 2. So 1.0916, 1 and 14/15, 1 and 35/37, right? There's all kinds of tiny numbers in here that are 1 and something, right? But they don't go all the way up to 2. For all of these numbers, the greatest integer less than or equal to all of these numbers is 1. So this number includes all the little pieces. Right? Because this is from 1.0000000 all the way up to a perfect 2. We're not including the perfect 2. And this is the greatest integer less than or equal to x. Okay? So if you write these two things down, it helps make sense of what it is we're trying to graph. On the x, on the x-axis, we're saying, hey, look at all these little pieces that are 1 point something, and the greatest integer that is less than that, that's confusing. The highest integer you can choose that is still less than this is 1, right? Because these are all 1 point something, so they all graph to this 1. Interesting. Now let's go up and do it for the next one. Let's start with 2.00000, and let's include all of the numbers that have 2 point something in front of them. 2.7934, 2 and 100 over 105. Write any number you can think of that starts with a 2 but doesn't go all the way up to 3. What is the greatest integer that's less than or equal to any of those numbers with 2 and some little pieces? Well, that's going to be 2. And the same thing up here. Let's say we want to say, okay, start with 3.000 and then include everything but not a perfect 4.0. Those numbers will all fall back to 3 as their greatest integer less than or equal to themselves. And we can keep going, right? If you want numbers that are positive but less than 1, their nearest integer will be 0, which is what this line represents. What about numbers that fall between -1 and 0? Okay, so -1, so it would be like -0.857, -14 over 17, numbers that are, they're negative numbers, so they're less than 0, but they are not as small as -1, right? So it's the same pattern. The x-axis shows all the little pieces, and the y-axis, or the function, shows what their value would be, right? So all these numbers that fall between -1 and -2, their closest number is, their closest integer is -2. What I want you to take away from this, if you can wrap your head around what we're doing here, that is great. But what I want you to notice is this interesting little pattern that emerges with the open ends and the close ends and the little lines. Greatest integer function, we're looking at all the little pieces of numbers, and then we're saying what's the greatest integer that's less than or equal to all of those little pieces, all right? It's confusing to say greatest that's less, but it's like go as high as you can with an integer that is still less than these numbers here. All right, there are no problems to do with this. I don't think, I haven't scanned the homework, but I don't think it comes up in the homework. But I want you to just have this in your brain so that someday if somebody talks to you about the greatest integer function and shows you this wacky picture, you'll say, oh, that is vaguely familiar. I think I've seen that before. And you'll be that much closer to understanding it. Guess what? We're done with 121. Yay! See you next time. Goodbye.